Hello everyone, welcome to Abhi online classes. Today I would like to discuss two topics. First one is absolutely convergent series and the second one is a conditionally convergent series. First we will see what is absolutely convergent series. A series sigma un is said to be absolutely convergent if the series sigma un is convergent. Once again, a series sigma un is said to be absolutely convergent if the series sigma mod un is convergent. If sigma mod un is convergent, then sigma un is absolutely convergent. We have to note down three important points. First one, for series of positive terms, the concepts of convergence and absolute convergence are same. For series of positive terms, the concepts of convergence and absolute convergence are same. But for alternating series, sigma un is absolutely convergent only if sigma mod un is convergent, which is obtained from sigma un by making all its terms positive. We'll see later one example. Third important point is every absolutely convergent series is convergent. Every absolutely convergent series is convergent, but the converse is not necessarily true. That means every convergent need not be an absolutely convergent series. Every absolutely convergent series is convergent, but converse of this is not true. We take one example. Given series sigma un equal to 1 minus 1 by 2 plus 1 by 2 square minus 1 by 2 cube plus and so on. Sigma mod un is, by making all its terms positive, 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus and so on. Obviously this is an infinite geometric series. By geometric series test, if the common ratio is less than 1, this is a convergent series. Obviously here the common ratio R is T2 by T1. Which is 1 by 2 by 1 by 2. It is less than 1. If the common ratio is less than 1, this series is a convergent series. So if this is a convergent series, this is absolutely convergent. So we take one more example. Test the convergence of the series sigma n is equal to 1 to infinity minus 1 whole power n by n square. We call this as sigma un. Sigma n is equal to 1 to infinity minus 1 whole power n by n square. Now we prepare sigma mod un. Sigma n is equal to 1 to infinity. By making all the negatives as positives, we'll get 1 by n square. We call it as sigma vn. We call it as sigma vn. Already we have taken sigma un. We take this as sigma vn. Here we observe this is an auxiliary series. Auxiliary series. By p-test, sigma vn, that means sigma 1 by n square. Since p here is 2, which is greater than 1, therefore this is a convergent series. If this is a convergent series, this is absolutely convergent. Therefore, sigma un is absolutely convergent series. Therefore, this is absolutely convergent. Now we'll see conditionally convergent series. Now we'll see conditionally convergent series. We call it also as non-absolutely convergent or semi-convergent. A series sigma un is said to be conditionally convergent series if two conditions are satisfied. What are they? Sigma un is convergent, sigma mod un is divergent. If sigma un is convergent and sigma mod un is divergent, if these two conditions are satisfied, then this series is conditionally convergent. We take one example. Consider a series sigma un equal to 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 and so on. This is an alternating series. It contains infinitely positive terms and infinitely negative terms. Here we write nth term as minus 1 whole power n into 1 by n plus and so on. This is an alternating series. To test the convergence of alternating series, we have only one test, that is Leibniz test. It has two conditions. Each term is numerically less than its preceding term. That means second term must be less than first term, third term must be less than second term, fourth term must be less than third term, so on. Each term is numerically less than, it is a monotonically decreasing sequence. That is the first condition. Here 1 by 2 is less than 1, 1 by 3 is less than 1 by 2, 1 by 4 is less than 1 by 3. Therefore, each term is numerically less than its preceding term. First condition is satisfied. Now the second condition, limit n tends to infinity un. Here the nth term is 1 by n. As n tends to infinity, 1 by n tends to 0. Therefore, limit un is 0. Second condition is also satisfied. Therefore, by Leibniz test, sigma un is convergent. Now we will see sigma mod un is divergent or not. Now we prepare sigma mod un from sigma un by making all the negative terms as positive terms. So we will get sigma mod un is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on plus 1 by n plus and so on. This is a positive series now. Now sigma mod un is equal to sigma 1 by n. This is an auxiliary series. This is an auxiliary series. Therefore, by auxiliary series test, which is also called as a P test, by P test, sigma mod un is divergent because P is 1. Here, P is 1. Therefore, this is a divergent series. For P greater than 1, it is convergent. For P less than or equal to 1, this is divergent. Therefore, sigma un is convergent. Sigma mod un is divergent. Therefore, sigma un is absolutely convergent. Therefore, sigma un is non-absolutely convergent, that is conditionally convergent. Once again I repeat, sigma un is convergent, sigma mod un is divergent. Therefore, sigma un is conditionally convergent, that is non-absolutely convergent, or it is semi-convergent. In this problem, a small correction is here, and the term is minus 1 whole power n minus 1. I request all the students to make this correction, minus 1 whole power n minus 1. Now we will see one more problem. Test the convergence of the series 1 minus 1 by root 2 plus 1 by root 3 minus 1 by root 4 plus and so on. Obviously, this is an alternating series. We call it as sigma minus 1 whole power n minus 1 un. 1 minus 1 by root 2 plus 1 by root 3 minus 1 by root 4 plus and so on. First term 1 by root 1. Second term 1 by root 2, third term 1 by root 3, fourth term 1 by root 4. Obviously, nth term is 1 by root n. This is greater than 0 for all n. un plus 1 is equal to 1 by root of n plus 1. Since root of n plus 1 is greater than root n for all n, 1 by root of n plus 1 is less than 1 by root n for all n. Therefore, un plus 1, here 1 by root of n plus 1 is un plus 1, is less than un. This is 1 by root n un for all n. Therefore, this is each term is numerically less than its preceding term, that is, it is monotonically decreasing. One condition of Leibniz test is satisfied. Next, limit n tends to infinity un equal to Limit n tends to infinity 1 by root n. As n is tending to infinity, 1 by n tends to 0. Therefore, 1 by root n is also 0. This is the second condition of Leibniz test. Each term is numerically less than its preceding term is satisfied. Limit un 0. Both the conditions of Leibniz test are satisfied. Therefore, sigma un is a convergent series by Leibniz test. Next, sigma modulus of minus 1 whole power n minus 1 un. Sigma modulus of minus 1 whole power n minus 1 un is 1 by root n. On applying the modulus, we take all these negative terms. We made all these negative terms are also positive. So now this is equal to sigma 1 by root n. This is an auxiliary series. Therefore, by P test, this series is divergent. Since P is equal to 1 by 2 is less than 1, here we write this as sigma 1 by n power 1 by 2. Here P is 1 by 2. That is less than 1. So for P less than 1, by auxiliary series test, that is by P test, this is a divergent series. Therefore, sigma un is a convergent series. Sigma mod un is a divergent series. Therefore, sigma un is conditionally convergent series. Or we can call it as a non-absolutely convergent series or semi-convergent. Next class we will see some more problems on this topic. Thank you.